Hello, Chem 213 students, and welcome back for our second video on amines. In this video, we're going to be covering chapter 22.4 to 22.7 of the textbook, which will mainly focus on reactions that can be used to prepare amines. Some of these reactions we've already seen before in previous chapters, but some will be new. For most of them, there are not mechanisms provided, which is unfortunate. That makes them harder to remember, right? But we'll talk about those. So in the last lecture, we talked about the physical properties of amines and also their properties in terms of acid-base chemistry and the fact that amines generally functions as pretty good bases and pretty terrible acids. Um, with amines having pKa's in the high 30s, but we saw that protonated amines, protonated ammonium ions, have pKa's in the range of 5 to 10, depending on the resonance stability of their conjugate base. Benzyl amines having pKa's around 5, whereas standard primary, secondary, tertiary amines mainly having pKa's around 9 or 10. Up to 11, rather 10 to 11 usually. So let's get started in talking about how amines can be prepared. So in chapter 7, we covered in Chem 212, we covered a variety of SN2 reactions with the cyanide ion being considered to be a quite good nucleophile. And so if we have a primary alkyl halide like this, we'll have just about only SN2 in our mechanism, primarily SN2. And so that would involve the nucleophilic attack on this electrophilic carbon. And remember, this carbon is electrophilic due to this polar bond in the to the halogen atom, causing this to be partially positive, being the electrophile, and of course the bromine is partially negative here. But the result is that because we have a primary amine with an open backside here for our open other side opposite to the leaving group for the attack here, and so we have the nucleophilic attack and the loss of the leaving group occurring simultaneously, and we get the installation of a cyano group. Important to note, this adds an additional carbon. So remember when thinking about synthesis and reactions, it's also always important to count your carbons. So here we do get one extra carbon by attaching the cyano group, but then we can reduce the cyano group using one of our standard reducing agents here, lithium aluminum hydride, followed up with water here, and then that will produce for us the amine. So this is a previously learned mechanism here, or mechanism and reaction for producing amines. In this particular one, remember that this amine will also come with the installation of an additional carbon atom, and it works best for primary alkyl halides. Preparing amines from carboxylic acids, we discussed this in the carboxylic acid chapter recently. So the first step here is going to be to use SOCl2, and recall that that is just going to produce a more reactive acid chloride, pushing this reaction along. After that, we treat with amine. Amine here is the ammonia, rather. Ammonia is in excess. Ammonia is going to now be the nucleophile that is going to initiate the reaction by attacking the electrophilic carbon right here. Again, electrophilic, as you guys well know, because of this very polar carbon-oxygen bond, causing it to be partially positive over by the carbon and partially negative over by the oxygen. This is followed by a step in which the carbonyl is returned and the chloride is expelled. So there's a second step, which I'll just put here in green arrows. After this lone pair goes up here in the oxygen, it comes back down and reforms a double bond, and a chloride ion leaves as the leaving group, and we get the amine. We can then reduce the carbonyl by using our good old-fashioned reducing agent here, lithium aluminum hydride, that we very often use, and follow this up with water. And so here we do not add an additional carbon atom, but we do produce another primary amine here. We can produce aniline, which is, remember, aniline is the name for a benzene ring with an amine attached. if we want to produce aniline, we would first um, install a nitro group on the benzene ring, and we can do that with treatment of nitric acid and in the presence of sulfuric acid. And then finally, we can follow that up in chapter 18, where we covered uh, aromatic reactions. Mainly, what they mentioned was they mentioned iron and zinc, and then with acid, and then a follow-up with sodium hydroxide, which is simply to deprotonate the amine. So once you do this first step, what you get is you get the amine, but because you have the acidic environment here, it's going to be protonated and have a positive formal charge to it. So the second step with the sodium hydroxide is going to be to deprotonate that amine, and that protonated amine, this protonated ammonium ion, and to get us now our ammonia. Now, also, what could be used as a very harsh reducing agent, more harsh reducing agent, is hydrogen gas with platinum as a catalyst. And this is possible to use, but remember, this will reduce all other. This will reduce carbonyls. This will reduce alkenes. This will reduce everything. And so, when we want to be selective and just reduce our amines, if there are other groups present, we'll definitely want to use this second synthetic route. So this won't be the route. The H2 platinum won't be the route we want to use if we have other groups to worry about that may be reduced, and if we don't want them to be reduced. Amines behave as pretty decent nucleophiles. Their lone pair here is pretty available to be given up. It's not as stuck on the atom as it would be for oxygen, for example. Although these negative alkoxide ions also behave as very great nucleophiles. Ammonia isn't negative, so it's not the greatest of nucleophiles, but it does function as a nucleophile. So if we have a primary alkyl halide, we know that, or here's a methyl alkyl halide, we know that those can readily undergo SN2 reactions in the presence of good nucleophiles. And this simply involves a backside attack opposite to the leaving group on a carbon that is the electrophile here attached to the halogen atom. Remember, partially positive over here in the carbon, partially positive on the iodide because of this polar bond. The leaving group simultaneously leaves in this SN2 process, and this will produce for us now a quaternary ammonium ion, or an ammonium ion with 4 bonds rather. And so now we at that point we can, if we are in the presence of any base, this will be deprotonated if it's pH, in the higher ranges, above 10 or so. Because the pKa of this is like 10 to 11, and so if you're in a basic environment that is pKa 10 or 11 or higher, which you would be here with the ammonium ion, you can then deprotonate, and there is an equilibrium here, right? Because you have the protonated ammonium ion too. This is going to give you NH4 plus, so there is a significant equilibrium here. This first step is reversible. And so then you will get the primary amine. So this is an efficient way to make a quaternary ammonium salt as well. You wouldn't use the last step here, the deprotonation, but yes. So one issue though with alkylating in this way is that when the alkylation is complete and you get here, going back, this primary amine, you still have this lone pair here, and this amine, this primary amine, can still function as a nucleophile. So if you have an excess of your, in this case, methyl iodide, or whatever your primary alkyl halide is, you're going to get a nucleophilic attack again. So we have another SN2 that results in the installation of another methyl group, and then we have the deprotonation again to return us here to the neutral amine, because this nitrogen with 4 bonds and no lone pairs now has a positive formal charge. We remove the proton here, we have 3 bonds and 1 lone pair, which returns nitrogen to 0 formal charge. However, it's still a decent nucleophile, so if there's more of the methyl iodide or whatever your primary alkyl halide is, it will go and do a nucleophilic attack again. At that point, the nitrogen, this lone pair will be used to make a bond, and so the nitrogen will have 3 bonds to carbon, 1 bond to hydrogen, giving it 4 total bonds and no lone pairs for a positive formal charge. And as long as there's methyl iodide remaining, this can continue, and then um, we'll get the removal of the proton again, and this is where we can create the quaternary ammonium salt, because now we still, with this tertiary amine, have a nucleophile that can attack, for example, in this case, the methyl iodide, another SN2 attack of the carbon, loss of leaving group, and here finally now we have the quaternary ammonium salt. It's called quaternary because this nitrogen is attached to 4 other carbons, and it is got 4 bonds and no lone pairs, so it has a positive charge. It's a positively charged ion, and so we have now, you know, tetramethyl ammonium iodide, basically 4 methyl groups on ammonium ion, now positive, and the negative ion is iodide. So this monoalkylation here, as long as we have plenty of the alkyl halide, will subsequently attach additional methyl groups or additional alkyl groups until you get a quaternary ammonium salt if you run this reaction with excess of your alkyl halide. We can also make amines via azide synthesis. And so azide here, this is going to be a nitrogen here, double bonded to a nitrogen, which is double bonded to another nitrogen. And this has 2 lone pairs. This has 2 lone pairs. It overall has a -1 charge. So here the sodium ion is positive. The azide is -1, and this is because, as we can see here, this nitrogen in the middle has 4 bonds and no lone pairs, so it has a positive formal charge. The nitrogens on the left and right have 2 bonds and 2 lone pairs, giving them a negative formal charge. And so altogether, this is a -1 charge on the ion. And so the azide ion can also behave as a nucleophile. And so we have a nucleophilic attack here on the carbon that's attached to the leaving group here, the halogen atom. The leaving group leaves, and this installs our azide, the azide component here. And then we can reduce with either hydrogen with a platinum catalyst or lithium aluminum hydride. Either of those 2 reducing agents will reduce us to the amine. Remember, lithium aluminum hydride being the softer reducing agent here. And so this will be one of the better ways to make a primary amine, because again, if we go and try to do it this way, we're probably not going to get the primary amine we want. Instead, we're going to get a quaternary ammonium salt, especially if we have an excess of the reactant. So this will give us a surefire way to get the primary amine, and this is probably our best way to make the primary amine, assuming that we don't want to start with a carboxylic acid. We don't want to install another carbon atom. If all we want is to take the alkyl halide here and make it into amine, this is a primary amine. This is a great way to do it. So here is that mechanism again, as I showed on the last slide. We have the azide do the nucleophilic attack on the carbon that is attached to the halide, which leaves as the leaving group. At that point, this is the remainder of the mechanism here. So you notice we have 2 additional nitrogen atoms that have to leave during this process. So when we're reducing with our reducing agent, for example, lithium aluminum hydride, a hydrogen atom will be donated to the nitrogen atom that's attached to the carbon, and we'll begin to reduce that. Then this bond will break here, or these electrons will move over and be positioned in the nitrogen. And so if we look at this nitrogen now that's attached to the halide, it starts with 3 bonds and 1 lone pair, giving it no formal charge. However, after this is done, it has another lone pair here. However, there's not a second bond here anymore. So now we have one lone pair and 3 bonds, giving this nitrogen atom 0 formal charge. The nitrogen here now has a lone pair and 3 bonds, so this nitrogen here no longer has a positive formal charge. It has a lone pair and 3 bonds, so it has 0 formal charge. But the nitrogen on the end still has this double bond and 2 lone pairs, so it has a -1 formal charge. At this point, the 2 of the nitrogen atoms are going to leave as nitrogen molecule. And the way that's going to work is this lone pair of electrons can be shown to be positioned here as the triple bond, and this sigma bond breaks, leaving a second lone pair here on this nitrogen. And so now this is going to leave, this right here is going to leave as, nitrogen gas N3, which is going to be neutral here. And what's going to be left here on this nitrogen is it'll have 1 bond to carbon, 1 bond to hydrogen, and it will have 2 lone pairs on it. So it's going to be an alkyl amide here ion. And at that point now it's got a negative formal charge with 2 bonds and 2 lone pairs. And so now we need to treat it with water to protonate it and produce for us finally the amine. And so we get a primary amine here by using the sodium azide and then following up with water, with a reducing agent and water, in this case lithium aluminum hydride and water. Another way of producing a primary alkyl halide or a secondary alkyl halide is from phthalimide. Phthalimide is this structure here, and something you're going to notice is that when it's deprotonated, so if we treat it with a strong base, we can deprotonate it like this. And when we do deprotonate it, notice that the nitrogen, which already has 1 lone pair here, it's not drawn, but it has 1 lone pair because it has 3 bonds here, 2 to carbon, 1 to hydrogen, so it has 1 lone pair. It has 0 formal charge. But after it's deprotonated, it has 2 lone pairs and 2 bonds, thus having a -1 formal charge. And notice that this negative formal charge is going to be extremely well stabilized. We have resonance. One of these lone pairs, pick any one, but this lone pair, let's say, is delocalized throughout this entire ring here. We have alternating double, single, all the way around. We have a number of resonance structures possible here for this molecule, and so this leads to fantastic resonance stabilization of this negative ion, which allows it to be the reactant for our reaction. So at this point now we expose it to a primary alkyl halide, and we have just a regular SN2 reaction here. This deprotonated amine here serves as a nucleophile and does an SN2 type attack on the alkyl halide, and this produces for us our alkyl phthalimide. And now we're going to treat this alkyl phthalimide to then release the primary amine and have the remainder left over. And in this mechanism, in this reaction, a mechanism is not shown. If you treat with an acid, this will decompose, where each of these 2 groups that was holding the nitrogen, what we have here attached to the nitrogen, instead becomes a carboxylic acid group. So we end up with OHs here and OH here to give us 2 carboxylic acid groups. And then we would have the protonated amine, which we could then deprotonate, or we can treat with hydrazine here. If we treat with hydrazine, we basically get the 2 nitrogens installed right here between these 2 carbons, between this carbon and this carbon, with 2 hydrogen atoms, and then we get the primary amine that comes off. And so using the use of potassium phthalimide is another way that we can produce a primary amine. If we do it with acid, we're going to get the protonated ammonium ion, and if we do it with hydrazine, we're going to get a neutral primary amine. We can also prepare amines through reductive amination, and so this is a reaction that we saw back in the ketones and aldehydes chapter 19, and this is no different here. So you've seen this reaction before. If we expose a ketone to in an acidic environment to an amine, the carbonyl here becomes protonated, and then that makes it more attractive to ammonia undergoing a new nucleophilic attack. That mechanism is again shown in chapter 19, and this produces for us an amine. That amine can then be reduced to give us the secondary amine, and so this will produce for us here a secondary amine. If the reducing agent is present, the amine can be reduced immediately. So if you have some reducing agent present, you can directly convert this amine into the amine. Reductive amination can be accomplished with a variety of reducing agents. So, you don't have to just use hydrogen with platinum. We've seen a number of other reducing agents, including lithium aluminum hydride and so forth. So, you don't, there, any of these relevant reducing agents that we've seen before could be used here rather than H2 and platinum. Sodium cyanoborohydride, which is similar to sodium borohydride, is commonly used because it's selective for amines. So again, another problem with using H2 platinum is you're gonna end up reducing alkenes. You're gonna end up reducing all kinds of other functional groups. So if you just want to reduce the amine to an amine, you would want to use sodium cyanoborohydride, which it's the same as sodium borohydride, but there's a H atom replaced with a cyano group. And this cyanoborohydride does not react with ketones and aldehydes in the way H2 and platinum would. So you can add it into the same reaction vessel during the amine formation and immediately form the amine. And so this is a specialized reducing agent that we would want to use for amines. So for reductive amination, this doesn't, unlike the other methods we saw for synthesizing a primary alkyl halide or even a secondary, we saw one example. Reductive amination can be used to yield primary, secondary, or tertiary amines. And so if we're starting with a ketone and we want to produce any amine, it's very simple. We just expose to the type of amine that we want to add on. So if we want to produce a primary amine, we simply use ammonia as the nucleophile to attack the ketone here. We expose to acid to protonate the ketone or the aldehyde, and we will use our selective reducing agent, sodium cyanoborohydride, and this will produce for us a primary amine when this nitrogen attaches to this carbon here. If we want to produce a secondary amine, we will want to use a alkylamine with one carbon attached to the nitrogen. And so then when the nucleophile nitrogen attacks right here, that nitrogen attaches, and it's not attached just to one carbon but to two, making a secondary amine. If we want to produce a tertiary amine, then we'd get we'd start with a secondary amine, and that, remember, that still is a nucleophile. It still has that lone pair, and so after we protonate this carbonyl, we can do a nucleophilic attack. So this is when this is protonated by the acid, it will do a nucleophilic attack and produce for us the amine, which we then reduce with the sodium cyanoborohydride and produce for us now a tertiary amine, because the nitrogen was already attached to two carbon atoms. Now it's attached to a third. So in summary, we have a few new reactions for synthesis. Overall, we have three options to produce a primary amine. We can use treatment with potassium phthalimide, and we can use that as a nucleophile to attack a primary alkyl halide, and alternatively we can treat with hydrazine, where we can follow up with hydrazine here, and this will produce for us a primary amine. We can treat an alkyl halide with sodium azide. Azide here will be the nucleophile that attacks here. And so in this case, the nucleophile is, the phthalimide. Here, the nucleophile is the azide that attacks, and that's what produce. And then we have to reduce it with a reducing agent. Again, this could be any reducing agent. Hydrogen and platinum would work if you're not worried about reducing other groups. Otherwise, using a more specific or milder reducing agent, and that will get us a primary amine. Alternatively, we can do a reductive amination where we take some amine and a carbonyl of some kind, an aldehyde or ketone, and then again we're going to protonate the carbonyl to make it more attractive here for this as a electrophile, uh, and we'll do a nucleophilic attack, and then we'll use a selective reducing agent, sodium cyanoborohydride, to finally reduce it and get ourselves the primary amine. Um, if we want to, if we if we want to do create secondary or tertiary amines, what we do first is we create a primary amine, and we can perform a reductive amination. Uh, just the same here, this reductive amination, we can perform this on a primary amine to make a secondary amine. We can then perform it again to make a tertiary amine, and then we can alkylate the tertiary amine to produce a quaternary ammonium ion. And so that is a summary of the additional synthesis possibilities that have been provided to us by these new um, uh, amine synthesis reactions that we have learned in this chapter. And so that's going to be it for the material that's going to be out for this video. We'll continue in this chapter on amines in the next video. Have a great day, and I'll see you next time.